to my lecture today. Of course, I'm actually going to use this opportunity to say we are done with linear regression. Okay, before now, I think I walk you through the simple linear regression and multiple linear regression, But today, the focus is going to be on another regression class that we call logistical regression model. And of course, this can be found in chapter 9, 10, and 11 of the recommended textbook. Okay, so in the outline, I'm going to introduce you to what I call simple binary logistic. How do we assess logistic regression model? Then I'm also going to walk you through the multiple linear, then likelihood ratio. I mean, the multiple logistic. This guy here should be, give me 1 second. I wanted to say this, okay? Multiple logistic, okay? Then I'm going to walk you through the likelihood ratio, then the steps involved in the analysis of logistical regression model. Okay, so let's get started. You know, I'm actually going to start with the example. Okay, let me tell you this. The nature of the response variable will determine the regression type. I'm going to say that again. What determine the type of regression to use is the nature of the response variable. When the response variable is quantitative or continuous, of course, we've been trying linear regression, right? But what of in a situation whereby the response variable is categorical? What do I mean by categorical? Like whether or not a person smokes. That's categorical with two levels. So in that situation, I'm actually going to have two levels, non-smoker and smoker. Okay. Now, what about the success of a medical treatment? Okay. Unfortunately, it is not all patients that's actually um, going to have a successful medical treatment. Okay. So why here is either is a patient survive or dies. Okay, that's two categories, right? Then we refer to this as a binary response. So by binary response, we actually trying to say we got two levels in the categorical response. Okay, but let me tell you this. In opinion poll responses, where we got agree, neutral, disagree, that is no longer binary response. Okay, we got three levels involved. Okay, we call this ordinal. Why is it ordinal? This is ordinal because two reasons. Number one, um, the levels is more than two. Number two, these are ordered. Ordered in the sense that neutral is going to be less than, disagree is going to be less than neutral, and neutral is going to be less than agree. So this is being ordered. Okay, so uh, take a look at that. Now I want to introduce you to binary logistical regression model. But let me tell you this. Why is it that we cannot use a linear regression in a situation where the response variable is categorical? I'm going to give you three reasons. Okay. Why we need to consider a new model called logistic regression for the purpose. The number one reason why linear regression can not actually be used when we are talking about modeling relationship between a categorical response is that there's going to be a violation of assumptions. What are the violations I will talk about in linear regression? There's going to be a violation of normality. There's going to be a violation of constant variance. Okay, and there's also going to be a violation of linearity. So how many violations are we going to have? Three, and that's not going to be good. How am I going to know whether these assumptions are violated? Of course, I've walked you through how you can investigate uh, violation under, we did that under regression diagnostics. Let me tell you this. Under linear regression, assumption is that error should follow normal, right? But here, error is not going to follow normal, but error will follow binomial distribution. You know, there's a probability distribution called binomial. We use it to model, you know, two possible, a random variable with two possible outcomes. Does that make sense? Then, when you talk about violations of linearity, okay, when you plot a categorical response, when you generate a scatter plot where you plot a categorical response against the explanatory variable, you are never going to get a straight line. Okay, you're actually going to have a form of a curve. Okay, that will be logistic in nature. Another reason why you know we don't use linear regression for categorical response is because there's a violation of constant variance. You know, in a linear regression, assumption is that the variance, okay, assumption is that the variance of y, if you remember what we've done before, the variance of y given x equal to days should be sigma squared, which is a constant variance. But situation where the response variable is categorical, I told you the distribution is no longer going to be normal. Okay, for binomial now, okay, if I talk about binomial, the mean of a because the process, each of them will be Bernoulli in nature, the mean is going to be P. Okay, this is theoretical statistics. The variance of a Bernoulli process is going to be P into 1 minus P. What am I trying to figure out? If you take a look at the variance here, the variance depends on the mean. Because in this formula here, can you see P? And the mean is P. Situation where the variance is depending on the mean. That's a violation of a constant variance. Variance shouldn't depend on the mean. Does that make sense? So in the case of a categorical response, where the distribution is Bernoulli or binomial, the variance is going to depend on the mean, and that's a violation. Now, let me tell you another reason why it is not reasonable to use linear regression for categorical response is that you're actually going to have a predicted range that will be nonsensical. You know, what should be the range? You're actually going to go over the range of 0, 1. Your prediction will go over the range of 0, 1. Because when you're talking about binary response, we're going to code a level as 0, we're going to code another level as 1, right? So when you make a prediction using linear regression, okay, you're actually going to get a prediction that will be outside the range. And that doesn't make sense, okay? Because the straight line is going to assume forever, right? But we needed something like a curve that will restrict the range to 0, 1. Does that make sense? Okay, and that is why logistic regression model is going to come in. Okay, so your Y is a binary response, your S is quantitative predictor, and we're actually going to have a pi. You know what we mean by pi? Pi will be the proportion of sources. Okay, now I'm going to show you the model. Please pay attention. What I'm displaying now is we have two forms of a logistic regression model. Okay, now this is the first form. We call this a logit form. What do you see here? Okay, this is a log of the odd ratio. What is odd? Do you know? I said pi. If pi is a probability of yes, 1 minus pi will be probability of no. So when I say odd, it means the ratio of two things that are conflicting or that are opposite to each other. So the log of the odd, okay, the log of the odd ratio Pi is the probability of success divided by 1 minus pi probability of failure. So what we're trying to say is that in a logistic regression, the log of odd is linearly related. I'm going to say that again. Why? Why is not linearly related? But you know what is linearly related? It is the log of the odd. Okay, I'm going to say that again. Log odd is linearly related. Okay, now this is a logistic regression in a logic form. Now, I also want to give you logistic regression in probability form. Please, I need you to pay attention. You know what we did? Do you know we can derive the probability form from the logic form? All what we're just going to do in the logic form is to solve for pi. Does that make sense? There are two forms of logistic regression model. The first one is in logic form. The second one is in probability form. You know, we use, for instance, in medical diagnosis, because we use logistic regression in a classification problem. We are a doctor may want to classify, some individuals into having a disease or not. Okay, pi here represent in a probability form. Pi represent the probability that the patient will have the disease. So what we're trying to say, the probability that the patient will have the disease actually depends on X. Maybe X may be height or blood pressure or and so on like that. Does that make sense? So we have two form of, so this is another reason why we cannot use a linear to model categorical response, because there's going to be an interpretation issue as well. The way we interpret parameters in a linear regression model will be different from the way it's going to be interpreted using logistic regression model. Is there any question moving forward? Is there any question? Now, okay, go ahead. Let's say for instance, I ask you to write a feeder model. If I'm not specific, you can write it too. But if I say, write the logic form of a logistic regression, I'm expecting this guy. If I say, okay, write the probability form, then I'm expecting that. But if I'm not specific, then you should write it too. Have I answered your question? Okay. Now I want to move right now. But you know what I'm displaying now? This is a simple binary logistic. Why is it called simple binary? Because I only have one explanatory variable. We can also have multiple binary. The word multiple will indicate that I have more than one explanatory variable. Does that make sense? Okay. Now, now how do we do it? How do we do this in R? Okay, this is what part of what my TA is going to walk you through. In R, please, I need you to pay attention to this code. You are no longer going to use LM anymore. You're going to use GLM. Okay? You're going to use GLM. Okay, generalized linear model. Okay? Now, and you're still going to write Y on S, here gender is categorical, right? Okay, gender on height, right? Then you must also indicate family equal binomial in the code. Does that make sense? That you have to write that all the time when you actually want to run a code. Then you do the summary, okay? And at the end of the day, I'm actually getting this output. This is the way the output is going to look like. I need you to pay attention to this output. Is kind of different from the linear regression. Can somebody spot the difference? Can you compare this with what you've been doing before? What is the difference? What do you see? Exactly. Send me a message for extra credit. Is that what you also wanted to say, right? I can read your mind. Send me a message for extra credit too. Okay. Now you're actually going to see a Z value instead of a T value. Does that make sense? Okay. Now, but how do we combine the estimate? Okay. I need you to pay attention to something. I got this kind of model. Of course, I'm actually going to be needing the values under the estimate, the same way that I also need them in linear regression. But let me tell you this, in a linear regression, we call them estimates of regression parameter, right? But they get a different name here. You know what we call them here? Log odd estimates. We call them log, please write it down. They are called log odd, log odd, log odd estimates. Okay, they are not just estimate, they are log odd estimate. Okay, I need you to pay attention to that. Okay, now if I want to write it in a field, oh my God, what am I writing now? I've already this is a probability form, right? What have I done? I've already plugged in the estimate. Okay, can you see that now? And I'm actually going to define what my pi means. Okay, let me tell you this. If you take a look at this gender, okay, arrow, we automatically, you know, if I go back a little bit, I actually want to do something now. Okay, now arrow will give you the idea of what the pi means. Okay, but the pi is going to be one of the levels of the gender. Okay, which is going to be like here we say, oh, the probability of yes, or the probability of female. Okay, the probability of females. Now you know what I want to, you know what I'm going to use this model to do. Do you know I can use this model to determine if I know the height? Let's say, for instance, I did not see an individual. Maybe I close my eyes and somebody give me the height. If I put the height into the model, I can determine the probability of that individual being a female or being a male. That's what we need this one for. That's what we do in hospital. We are maybe you check the blood pressure and the doctor want to see whether the patient has COVID. Okay, because there was a time they send my children, what they send them home during the COVID time. They said their BP was so high. Okay, even though they've not tested, but they believe they've not tested them, though they believe that the probability of having it is actually high based on the BP. Okay. Now, this is the probability form of the fitted logistic. We can also write the log odd form as well. Now, let me tell you this. We know where I want to go now. How do we assess our logistic regression model? Just like in a linear regression model, we know we learn when we put a model in place, we normally want to investigate how valid is the model, right? That's what we mean by assessing the model. I'm using a different data set here, and I started this directly from the textbook, recommended textbook we're using. You know what I'm trying to do here? Maybe you're looking at the effect of GPA, okay, GPA on passing of of passing an exam. You said that somebody passed an exam or somebody failed an exam, right? Okay, which is binary, right? Okay, now I have this outputs from R. Okay, now when I have this output from R, if I want to assess the model, what I'm going to assess, I'm actually going to test the slope, okay, as well, just like the same way we did in a linear regression. But let me tell you, we're no longer going to be focusing on T. You remember in the linear regression, it was test T test, which is standard error divided by, the estimate divided by the standard error. We're also going to do the same here, okay? But it's not going to be T, even though it's going to say it's still going to be the same formula, but it's not going to be T, but it's going to be Z. Because in statistics, we got a T distribution, we got a Z distribution. And we can also talk about the confidence interval too. Okay. Whether I want to talk about confidence interval or I want to test hypothesis about the beta one, the other guy is a confidence interval. Okay. And this guy is a test, that. And let me tell you this. What are we actually testing? Do you know the when beta 1 equal to 0, you know what that means? When beta 1 equal to 0, then you are trying to say intercept model. Does that make sense? When slope is 0, then that means intercept model. When you say intercept model, you know what that means? You're trying to say passing exam does not depend on GPA. Okay, but take a look at this one in the alternative where you say it is not equal to 0. So where it is equal to 0, this is the model now. What has happened? You know the way the model. Okay, let me first explain this. Let me walk you back. Okay, sorry. You know this is a model, right? That's a logistic regression model, right? That's a full model. Okay. When beta 1 equal to 0, what happened? It becomes this guy. That's an intercept model. So this guy is an intercept form of a logistic model. That guy is a full model. Does that make sense now? Okay. Now, and if we are testing, okay, what we normally need to pay attention to is the p-value. Do you see the p-value right now? Okay. When the p-value is less than any reasonable level of significance, we're actually going to reject the non-hypothesis. Now, I'm going to leave you now to multiple logistic model. Oh my God. Look at this. This is a logit form of a of a multiple logistic regression model. What happened here? This is an extended form, right? And this is the probability form. Take a look at that. Compare this now to this. Can you see this too? This is the simple binary logistic. Okay. Why the other one now that I just show you right now is a multiple binary logistic. So where we are now, this guy here, okay, this guy here, okay, this is a multiple logistic regression. Why multiple? Because we got S1, we have more than one explanatory variable. But let me tell you, the response variable is still categorical. It's still two levels. Does that make sense? Okay. Now, what I'm going to show you now, please, if you don't understand, ask question. Um, in a multiple logistic regression model, how do we test between an intercept and a full model? If you want to test an intercept, you know what you're going to do? All the slope is going to be 0. Do you see that? B1, B2 up to BK equal to 0. Okay. This is like, you know, yesterday when I was walking you through, oh, sorry, I think maybe on Monday when we did F-test and partial F-test, you know what F-test does in a linear regression? We compare an intercept model with a full model, okay? While the partial F-test, we compare a simple model with a complicated model. So here too, in a logistic regression, we also have a way to compare, an intercept model with a full model. Okay, so the intercept in the non-hypothesis or the slope is going to be 0. If beta 1, beta 2 up to beta k equal to 0, then it means that's an intercept model. Okay, now I needed to pay attention now. You remember when I was testing this under linear regression, it was F-test. But now under logistic regression, it is not called an F-test. We normally call it a G-test. Take a look at that. Okay, G equal to that. You know what you're actually seeing now? The mathematically it is negative to the log of that L0 means likelihood when the non-hypothesis is true. What is the non-hypothesis? The intercept model. Then L is likelihood when the alternative is true. And you know what? The non if I want to rewrite this guy currently is in mathematical form. If I want to write it in another form, then I'm actually going to say, oh, I'm testing reduced model against full model. Does that make sense? Okay. Now, how do we do that in R? Please, I need you to pay attention now. Okay. Now, the analysis when you are comparing candidate model within logistic framework, okay, then we're actually going to use what we call LRT. What do we call LRT? Likelihood ratio test. Okay, likelihood ratio test. Now, for instance, I actually want to work on grade. Okay, I actually want to work on, grade. And if I want to have access, I load this package. Okay, and my data is from online. Take a look at this. This is a great data online. You can see HTTP, right? When you copy that into R, and you do names into grade, it's actually going to show you all of these: age, travel time, study time, absences, grade one, per grade one, per grade two, and final grade. Maybe you know what we want to do here. The response variable is the final grade, and we're actually looking for a very good explanatory combination of explanatory variable that would determine final grade. We want to say, what is the role of age of student in a class? What is the role of travel? When people travel, so students travel a lot. How does that impact your final grade? Or what about study time? What about absences? And what about maybe your midterm 1 grade and the midterm 2 grade? Okay, so if I really want to tell, okay, I'm actually going to compare between using a simple model and a complicated model. Okay, now I'm going to show you what my simple model is. My simple model say, okay, you know what? Okay, the only thing that could affect final grade is absences. That's a simple model, just one explanatory variable. But the complicated model, oh my God, the complicated model consider a lot of variables. Now, this is very similar to what we did in the linear regression, where we use partial F-test, right? We use partial F-test when you are comparing a simple model with a complicated model, okay? And the code was ANOVA test, right? ANOVA into simple, comma, the complicated. But in the case of a logistic regression, the analysis is actually likelihood ratio test. Okay, now take a look at this now. You see what I wrote here? Okay, LR test instead of ANOVA test that we use in linear regression. LR test nested, so complex. This guy here, simple, is nested. What do I mean by nested? Of course, you can see this guy is also okay. Let me tell you this. Do you see this model? It's nested in the complicated too. This is what I mean. That's what we call nested. The simple model has to be contained in the complicated model. Okay. Now, and I told you the first one here that I call nested. I'm actually referring to simple. The complex here, I'm actually referring to the complicated. Does that make sense? Okay. Let's see the way the arrow is going to display the results. Oh my God. The arrow is going to display the result in this way. An arrow is even going to tell you your model 1 and model 2. You see, your model 1 is a simple model. Model 2 is complicated model. But you know what I'm doing here? You know what I first consider? I did not use all the explanatory variable. I first consider this. And let me see what with just 2 variables more, and I consider this first. Do you see that? Okay, and I can go all the way. Okay, but based on comparing one explanatory variable absences to 2 explanatory variable absences and age, let's see what the result is going to. This is the result. Now, all what you need to do, pay attention to the p-value. What happened now? The p-value is less than 0.05. When a p-value is less than 0.05, you know what that means? Reject the simple model. When you reject the simple model, your conclusion will be in favor of the complicated model. What you are trying to tell the world right now is that, we need more than absences. What you want to predict or what you want to explain, final grade. Does that make sense? And when you take a look at the output, please pay attention. The other time I was talking about likelihood. Look at this. Do you see that? If I ask you in exam, give the log likelihood of the simple model. The log likelihood of the simple model is negative 1678.7. The log likelihood of the complicated model is negative 1675.8. Okay, please pay attention. Now, do you know? Okay, now this is another one. You know what I'm doing here? Here, what am I testing? I'm testing the effect of your midterm 1 and midterm 2 grade on the final. And in the complicated model, I'm looking beyond that. Okay. What is the difference between, here? I'm talking about looking at the effect of study time and the midterm 1. But here, what is that? That's an extended, right? I'm looking at the effect of study time, the first grade and the midterm 1 and the midterm 2. Can you see that? The two of them, what distinguishes between a simple model and a complicated model is that in a simple model, you have fewer numbers of explanatory variables. In a complicated model, you got more. Does that make sense? Now, uh, do you know what you are seriously testing between these two? Okay, what you are actually testing is this. Does that make sense? That's what you are testing. That is a major thing you are testing because study time and per 1 grade is also inside the complicated. And if the regression coefficient for per 2 grade is equal to 0, what happened? Then you're going to go back to the simple model. Does that make sense? Now, uh, you know, like I said, you're going to write that LR test into simple, complicated. Let's see the result. This is the result. Okay, this is the result. And if you take a look at this, you pay attention to the p-value. Okay, what happened now? The p-value is less than 0.05. Then you're actually going to reject a simple model and you conclude in favor of a complicated. Is there any question on this at this time? Okay, you know, we don't just do what we do. We got reason, for what we do. So this is to show the world we're not just choosing model, but we actually get a threshold. Okay. Now the next thing I want to do now, I want to go into steps involved. What are the steps that are involved in the analysis of logistic regression model? And you know what? I'm going to visit a bank right now. Okay. I want to visit a bank. You know what this bank want to do? This particular bank want to figure out what is the chance that if a customer should request for loan, what is the chance that the customer is not going to pay back? That's a probability of default, right? Do you know that the bank really want to build a model? They are seeking the assistance of statistician to build a model, and they're gonna use their available data on the model. And if the model is going to do a great job, a new customer that is coming, right? And if the new customer is seeking for a loan, they actually are going to make a prediction on whether it's going to default or not. But you know what? We got a data set. The bank currently have this data set of 10,000 individuals, and that data set actually have these variables. Okay, some of them default, based on the record in the bank, the customers, right? Some of them default, and some of them did not. And some of their customers are students. Then we're also going to look at the balance. Then we're also going to look at the income. Of course, when you are opening a bank account, I want to believe bank will actually get all of this information. Now, how do we help this bank out? This particular bank actually want to figure out, they want to generate a model that will make them to do a classification of their customers, whether they're going to default or not, when they ask for loan. Now, the very first thing you're going to do, you want to have access to this data set that I'm talking about. Okay, load a package ISLR in R. My TA is going to walk you through all of that. And let us four of us do some descriptive analysis in the data. Let's understand the data set right now. That's what we're doing here. When you do the summary of the data, it's trying to tell you the fault, which is a response variable. It's telling you on out of the 10,000 customers in that bank, 9,667 have not defaulted. Why 333 have defaulted? Okay. Then 7,056 are students. I'm talking about their customers right now. And 2,900 2,944 are students, and 7,056 are non-students. Then you can see balance and the income here are quantitative. You can see the minimum balance, maximum balance. You can see the income. Okay. And of course, I got 10,000 individuals. So this is going to be the first thing I'm going to do. I'm going to load my data set, and I'm actually going to conduct a descriptive statistics understanding my data. Now, the next thing I'm going to do, please pay attention. Okay. What we're going to do, we're actually going to split our data. We're going to split data. Okay. When you are doing a classification problem, or we are doing something that has to do with prediction, we actually need to split our data. You know, the 10,000 individual actually going to be split into training, data set, and the test. And we normally make sure that a good number of the individual will be committed to training. So what do we want to do with the training? We're going to use the training data to learn about the model. And we're going to use the test data to test the performance of the model. Does that make sense? And you know what? When you're doing that, you need to set a seed. Setting a seed will make the word reproducible. For instance, if I have 10, if you guys are working with 10,000 data and I ask you to split 70 to 30, what you're going to have in your data will be different from what you're going to have in this data. But if we want to have the same data, we set seed, and we put the same number when we set seed. One, if I put one, if all of us put one, then what you're going to have in your training is what I'm going to have in my training. What you have in your test is what I'm going to have. Does that make sense? Okay. Now, like I said, we do 70, 30. Okay. If you take a look at this is the code in R. Okay. This is the code in R to do that. So the step number 2 is splitting your data. Step number 3, then we fit the logistic regression model. But we are fitting the logistic regression model to a new data. What is the name of that data now? It's actually going to be the training data. And that's why when you come here, what do you see? Oh my God. What do you see in the data? I said data equal to train. Okay, data equal to train. Can you see that? Now, data equal to train, and when I do this summary, I'm actually going to have this output. Look at the beautiful output we're having now. Can you see the beautiful output? Okay, now these are the estimate, right? But what did I call this estimate? Log odd estimate. Don't forget that, right? This is a p-value, right? Take a look at that. Okay, now we can actually interpret, the estimate right here. Okay, and that is the interpretation that I actually put here now. Okay, okay, for example, if I want to interpret balance, okay, I want to interpret balance. Let's take a look at the balance. Okay, do you see this balance, right? Okay, want to interpret that. Okay, I said the coefficient in the output indicate the average change in the log odd. You have to mention log odd when you are interpreting. Okay, average in the log odd of the 14. Okay, for example, a 1 unit increase in the balance is associated with an average increase of that in the log odd of the 40. If you don't put in the log odd, then you are actually misinterpreting. Does that make sense? In the log of the 40? Okay. Then the p-values in the output also give us an idea of how effective each predictor variable is at predicting the probability of default. Okay, so are you surprised? I need you to take a look at this guy now. Why do we have a student? Yes. It means R has automatically coded students, being student as 1 and not being student as 0. That's why student yes is coming in the output. Don't forget, what we did before. Okay, now, how do we assess the model? In the case of logistic, we don't use R squared, but we use something that we call Ferdinand squared. Okay, so that is what we use, and we believe the values also range from 0 to under 1. So value close to 0 indicate that the model has no predictive power. Okay, and in practice, we expect values to be over 0.4 to indicate that the model you have fed actually commiserate and depict reality in the data set. Does that make sense? Okay. Now, let's how do we find that? When you take a look at the output, you are not going to see anything R square as part of the output. You are going to be the one that will compute that yourself. Oh my God. How am I going to compute that? You actually need to install a package. Do you see that? You're going to install a package. We call that package PSCL. Okay. Then you load it. Then that is a code together. What do you have here? 0.4. And what do we say? For a module to have a predictive power, it should be over 0.4. And this is giving us 0.47. And that was why we said, okay, you know what? That indicates our model fit the data very well and has a high predictive power. Is there any question here? Okay. Now, the next thing I want to do now, if you take a look at what we are doing here, that we are splitting data, is because of the fact that we are interested in prediction. Okay. Now, we can also talk about variable importance. Okay, among the explanatory variables that we use in predicting defaults, okay, can we have a way to rank them? Okay, now, all what you just need to do, you need to install a package called Caret. Then you do VARIMP. That's a variable importance. Okay, now the variable, oh my God, take a look at this right now. Okay, the most important variable is the one, look at the value, is balance, which is true. Before the bank will even consider giving you a loan, they're actually going to look at your balance, your account balance. Okay, then the next one is whether you are student or not. Then they're also going to talk about income. That's a variable importance. Now, let me tell you this. Just like in the conventional linear regression, the moment you have more than one explanatory variable, okay, you need to watch out for multicollinearity. Okay, you also need to watch out for multicollinearity here. And I told you, how are you going to investigate for multicollinearity? Okay, in logistic regression, you actually need to load install a package called car. You load it, then you do VIF. Okay, you remember the way we did it? The VIF means variance inflating factor. And don't forget, I told you we got a threshold, right? We got a threshold, right? When VIF equal to is more than 5, then it means there's a problem of multicollinearity. Okay, what is happening now? Is there anyone greater than 5? Is there anyone? No. Look at that, 2.574. Look at the balance, look at the income. There's no problem of multicollinearity. That's what that means. Now, what is the next thing I'm going to do right now? Oh my God, because there's no problem of multicollinearity, I can think about using the module now to make predictions. Okay, now don't forget, if I want to make predictions right now, okay, for instance, I want to make prediction for 2 individuals. Okay, define 2 individuals. Okay, now take a look at this. Maybe let's say somebody is coming in. Okay, somebody is coming in. I got a new customer right now. And what I want to do with a new customer is this customer is not in my data. Okay, and this customer has actually been with us. These customers have not taken loan before. Okay, it's our customer. Okay, now we look at the balance on the account. The guy has 1,400. The income is 2,000 maybe per month. And you know, we actually want to predict, don't forget, the student could be yes or no. The probability of defaulting now. Okay, now if you take a look at this, okay, do you know why there are two individuals? We're considering a student that have a balance of 1,400 in account, and that student has income of 2,000 per month. Then we also have another individual in the bank. It's not a student. That's why you see yes and no. We're considering that together. We got that make it two individuals. But these two individuals, they got the same balance and they got the same income. But you know what? Are they going to have the same probability of default? No. Look at that. The probability of default now, you see that? The first one for student is 0.027. And for the other one is a zero individual that is non-student. They also have the same account balance and the income. Does that make sense now? Okay. Now we want to go into step 5, model diagnostics. We need to do model diagnostics. I just make a prediction for this individual, for these two students, but I'm not going to come here. This is just like I'm just testing for two individuals. Okay, but if you take a look at this, I seriously want to do model diagnostics. Okay, and I want to see how well my model perform. Okay, but if I want to do model diagnostic, you know what I'm going to do? Model diagnostic, I'm actually going to use the data set that I have in the test. Don't forget, I split my data before, right? I actually, I train my data and I train my model with my training, the data in the training set. But right now, I want to use, and let me tell you this. I already know the status of the data in my test. I know some default, some did not. But right now, I want to use my model to do that. Take a look at this now. That's a test, therefore. And at the end of the day, take a look at this. Optima now is giving us a 0.54. And what is the meaning of that? Okay. This tells us the optimal probability cutoff to use. Because if we want to make a decision, we need a cutoff. What cutoff are we going to use? Okay. Now, is that so? Any individual with a probability of defaulting of that or higher will be predicted to default. But if it is lower, this is like a threshold. This very threshold, we created that using the test, using the data set in the test. Does that make sense? Okay. Now, the next thing that I'm going to show you now. Oh my God. We need this guy a lot. This is a confusion matrix. I'm going to tell you what confusion matrix means. Okay. Now, take a look at this. Confusion matrix between your test, those that are your test data and the predicted. Okay. Now, do you know the meaning of this? According to, that means this is trying to say 2,912, right? They did not default. In the data, they did not default, and your model correctly identified them not to default. Okay. Now, I need you to take a look at that and this. Let's talk about the diagonal. Diagonal is accuracy. Okay. 39 did not default in the data, and the model predicted that. But let me tell you this. Let's talk about the error. Error of classification is this guy. That is the error of classification. Do you know what 64 actually talking about? Okay. They did not default in the data, but the model predicted them to be default. Okay. So the left diagonal is actually an error. Okay. We can rule out errors. Okay. And if you really want to understand this, you can look at the sensitivity. What do we mean by sensitivity? The sensitivity is the ability of a model to detect when something is positive, it should detect it to be positive. Why specificity is when it is negative, it should detect it to be negative. But the moment it detects it to be something else, that will be a false positive or a false negative. Now, if you take a look at this guy now, that is the sensitivity, and this is the specificity. But let me tell you this. When one is high, the other one is going to be low. It now depends on, you know what the first one is saying? The first one is saying the probability of an individual, okay, that default, okay, the probability of a model detecting that individual is that 0.37. But if somebody is not going to default, the probability that the model will detect that is not going to default is actually high. Okay, then we need to calculate the next one. To calculate the misclassification, the total misclassification error rates. But if you take a look at this now, the total misclassification error rate is very, very small. If you really want to know in percentage, what is that? Multiply by 100, that would be 2.7%. Yeah, your model is okay. Is there any question? That's how we do it. Is there any question? You know, our models are not failing us, but maybe we are the one that we're not doing the right thing. Don't rush to using model for prediction. Make sure you actually evaluate your model. Make sure you subject your model to diagnostic testing to make sure we got criteria. You can see a lot of the criteria we've been using today. Okay, so this is going to be the end of this material, and of course we're not meeting tomorrow because of independent anniversary. Of course, you're going to have your lab on Friday, and the next time I'm going to meet you is going to be on Monday. Okay, why you make sure you enjoy your anniversary. Stay safe. See you on Monday. Bye for now, everyone.
Thank you. Have a good weekend.
And you too. You're welcome. Stay safe.